Okay, thank you very much. If no more questions, then I'd like to call on the stage Dr. Christoph Rehbock from the University of Duisburg, Essen.
Okay, welcome everybody to the last talk of the session. Here I'm going to give a bit of a general overview on toxicological assays from the viewpoint of a material scientist. So I'm not so much into biology, but material science. Okay, when we look at the literature on toxicity of nanoparticles, one can conclude that this topic has been extensively studied. When you look, for example, at the example of gold, you can see that there are at first an increasing number of publications and citations in the last 10 years. And we can see that about 700 publications have been dedicated only to the topic gold nanoparticles and toxicity. So one would assume that actually the topic should be quite well understood, as there's so many people working on it. However, when you look at different examples, sometimes the opposite seems to be the case. So when you look at toxic effects which were observed by different researchers, some said biocompatible, some said found some multiple adverse effects, others said it's unclear. So the question is, where does this diversity actually come from? One could argue actually that it may be due to different biological systems tested, but there can also be some shortcomings on the design of toxicological assays, something which I want to address and talk about a bit in the next few minutes. So the different effectors influencing toxicity tests, which are actually first the particle dosing, so how we dose our particles. The second one I want to talk about is the exposure scenario and the ligand effects. And the third one are actually the biological system. Okay, let's first start with particle dosing. Okay, when we look at most toxicological assays, what we find is actually the current standard in toxicology are mass doses. So we always administer a certain mass per volume, or actually the atomic concentration of the for example, the metal of the gold. This is established for low molecular weight or for particles with atomic concentrations. However, what is the information or the informative value for particles for nanoparticles? Let's look at a simple example. We have just two fractions of particles, large particles and small particles, and we want to study the size-related toxicity. When we look at the properties of the material, first we can see that down here we have a lower surface area and a lower number, but here we have a high surface area and a higher number. Let's make the simplest possible outcome. We find that actually the larger particles are more toxic. In this case, we can clearly see, okay, this is a size effect. However, what is when we find that the smaller particles are more toxic? Actually, we do not know anything, actually. Because it can be dedicated either to the size, to the number of the particles, or to the surface area. So apparently the informative value of mass doses in nanotoxicology seems to be limited. To further illustrate this point, we made a calculation and showing how many particles are actually found when we have equal mass doses for 50 nanometers and, for example, for 1.4 nanometer particles. And you can see from these numbers that actually when we reduce our particle size from 50 nanometers down to 1.4 nanometers, the amount of particles in the system increases by 4.5 orders of magnitude. So this is a massive amount of particles, massive change in particles. This can be best illustrated when we take a look at the surface coverage, which is shown in this last line. For example, when we have our 50 nanometer particles, we can say that about 14% of our cell surface is covered by the particles. However, when we go to the smaller particles, the 1.4 nanometers, we actually go to 500%. This means when we take small particles, they cover the surface of our cell by a factor of 5, so 5 more surface area. This can actually be dramatic, as the complete cell will be completely covered by these particles. So this means that actually based on these data, on mass dose, we cannot determine whether smaller particles are more toxic or not, or whether it's just a surface effect. So we can conclude from this actually mass dose inadequate for systematic toxicological assays in nanoparticles. So what can we do instead? we can use, for example, the number dose. We just dose at equal numbers. In this case, we have for the larger particles a higher surface area and a higher mass, and for the smaller particles a lower surface area and a lower mass. Okay, when we do it again, we took a look at the simplest possible outcome. When in this case the small particles are more toxic, it's clearly dedicated to size. However, when the larger particles are more toxic, we again don't know whether it's a size or a surface area effect. So the result or a solution could be actually, why not dose at equal surface area? When we do this, for example, we may have slight differences in the numbers, but in general, we can say that actually when one of these fractions is more toxic, we can clearly dedicate this to a size effect. So this is not only true for this simple example, but this has also been established in literature. For example, when we look at this example of the inflammation of rat lungs by titanium dioxide nanoparticles, there were actually two types of particles studied, one 20 nanometers, the other 250 nanometers. And when you only look at the mass doses, you would really assume, everyone would say, well, smaller particles are obviously more toxic. However, when we plot this as a mass dose, which is shown here, we can clearly see that actually apparently it's not a size effect, but it's just dedicated to the particle surface. These results have actually already been published by Oberdörster et al. In 2005, so it's already been 10 years since these results have come up, and it's already well established, for example, in aerosol toxicity. However, this has not been adapted to colloidal nanoparticles so far. So I would strongly suggest that we do just that for the future. Also for colloidal nanoparticles, we take the surface area. So every one of you is of course aware of the fact that we cannot take the total surface area. We always have to reference this to the cell number. But maybe it's sometimes interesting not to take the cell number, but also when you want to compare different trials, it's interesting to actually use particle surface area per cell surface area. In this case, we can, for example, compare the effects on small cells, like for example spermatozoa, or on larger cells as macrophages. So this is my recommendation for the particle doses. Okay, now we come to the second part, which is actually exposure scenario or ligand effects. How these two are connected, I'll come to this in a short time. Okay, when I talk about exposure scenario, I mean how do nanoparticles actually enter the body? For this, I want to talk about two different aspects. The first one is called intended exposure, where we actually inject a nanodrug into the bloodstream. What we have in this case is a nanoparticle with multiple ligand shells, something we want to have to study. When we enter these at different surface doses into the bloodstream, we should of course get toxicological information, which is actually interesting when we only want to study the property of one drug. However, when we want to do a systematic toxicity, we can never determine whether this effect comes from the nanoparticle or maybe from the ligand shell. We can never determine this. A second exposure scenario is actually the unintended use, which is, for example, of implant abrasion. We, for example, have an implant in our body, and this stays in there for months or years, and we have the problem that sometimes we have nanoscopic wear debris, which can be released into the system, and something which also has to be studied. In this case, what we have is actually a nanoparticle without any artificial surfactants covered by a protein corona. So in this case, we could also synthesize these materials. However, we have the problem that here we have, when we study this, we have a very time-consuming sample preparation. So what is needed to study both is actually a model system based on a ligand-free colloidal nanoparticle. Based on this, we can take this reference system and add any ligand we want, and then systematically study any influence of the ligand and clearly differentiate between particle effects and ligand effects. So the question is, how do we get this ligand-free colloidal nanoparticle? A solution could be the method of pulsed laser ablation in liquids. This method is actually a very simple procedure. We just put a piece of metal into a beaker, focus a laser beam on the target, move it with a scanner, and then we can fabricate our nanoparticles. We only have the metal target, water, and we need light, so we have 100% ligand-free nanoparticles, while the while the ligands can be added afterwards. So we have a very good model system. We use this to study the problem of implant abrasion, where we have nanoscopic vertebrae, where we can alloy nanoparticle with a protein corona. What we did, we took a ternary implant steel alloy out of iron, chromium, and nickel. We subjected it to pulse laser ablation liquid in the presence of albumin, or albumin was added close shortly after the process. And then we actually have our system, which is a protein-coated alloy nanoparticle, which mirrors the relevant species during implant abrasion. We further analyzed these particles, and by TEM-EDX, we studied single particles in this case, and we found that actually the target composition is retained in the nanoparticles. Here you see in black the composition of the bulk material, and in red the composition of the nanoparticle. Okay, let us sum up for this second part. The test, we can conclude that the tested nanoparticle always must be adapted to the exposure scenario, and ligand-free reference should be used to characterize ligand effects. Okay, the third part I want to go into is now the biological systems. Currently, the standard in many toxicological assays is still the standard live-dead assay. So for in vitro, this means actually just assessing cell viability, while in vivo, LD50, for example. Okay, this test assay system has some drawbacks, which is, of course, at first, cell culture experiments, when they only address the live dead, are difficult to transfer to in vivo settings. Subtle effects are often overlooked. So, for example, particularly for the gold, which is usually quite relatively biocompatible. And the concentrations are always go beyond any medical relevance. So what's the alternative? It's, of course, the functional toxicity. This is something which has already been shown by many speakers, that actually it's important to monitor functional parameters. You can, for example, look at the stem cell differentiation or the excretion of different metabolites, as it was shown by many of other speakers. But one other aspect, which I want to go into detail with in the last few minutes, is the area of reproduction biology and fertilization. Why reproduction biology? Because actually the cells we have here are actually very easily available. They always have a defined function, and the system is highly sensitive to different aspects. The system I wanted to study in more detail was the oocyte maturation. We took an immature oocyte, exposed it to nanoparticles, and looked at the maturation process, which was the meiotic state of the nucleus and the cumulus cell expansion. So what we studied here was the functional parameter, not the cell viability. The oocyte maturation is known to be the most sensitive parameter in this context. So we actually have an efficient, highly sensitive model for reprotoxicology screening based on functionality and not viability. Here are some results which we obtained. We changed the coating of gold nanoparticles. We added either only BSA or citrate and BSA. We also changed the surface dose, increased it, and we found actually no impact of the gold nanoparticles on our oocyte maturation. The only effects we found were actually when we added some silver to make silver gold alloy nanoparticles, and we found a toxic effect probably due to ion release. So we can summarize that actually the oocyte maturation is not affected by particle surface area and not by functionalization in the tested regime, but the oocyte maturation is non-linearly affected by silver-rich alloy nanoparticles. So to summarize my talk and give some recommendations on what to do, how to design toxicological assays, the first important thing is actually we always have to be very careful when it comes to particle dosing. So we always have to use the dose at equal particle surface area and always reference this to the biological system. Secondly, when we study ligand effect in different exposure scenarios, it's always important to adapt the nanoparticle to the exposure scenario. And I've shown you that when we want to study ligand effects, fundamentally, we have to use ligand-free references. And in the third part, I've shown you that functional assays are actually the most important for toxicological assays. So I want to thank, of course, all the co-workers who contributed to this project, our co-workers from the Friedrich Loeffler Institute who helped us with the reproduction biology studies, And of course, I thank you for your attention.
Any questions? All right, then let me finish this session with maybe the last question. Talking about practicality, from which species did you get the oocytes? Is it a practical assay for toxicity?
It was actually porcine oocytes, which were isolated taken directly from our abattoir. So we really took them directly from the abattoir, and we just then cultivated them. So it's actually quite an easy assay.
But to get these oocytes, it looks like very unique.
Yeah,
unique source.
We had actually a good connection to the abattoir, actually, where we could get the oocytes, and then we were able to isolate the oocytes from the ovaries, pig ovaries. It was kind of work, of course, but it was not as difficult as it sounds. So.
Well, anyway, thank you very much.
Yep.
And we are right on time for the break, but we kind of missed the formal discussion. So let me ask the audience if anybody has a question to any particular speaker, or a question, a general question, which one of us speakers could address. So that if not, then it looks like it has no sense to come up to the front and sit. So then let me thank you for your attention. Let me thank the speakers for the very nice and interesting talks, and the audience for your interest and presence. Thank you very much.